Hello, Psych 101 students. In this video, we will cover learning objectives 1 and 2, looking at how does your nervous system work. So let's begin. Your nervous system, as it says here, is the basis of your mental activity and behavior. And it's a network of billions of cells in the brain and the body responsible for all aspects of what we feel, think, and do. So your nervous system is responsible for every behavior you do, every emotion you feel, every memory you store, every thought you think, all the personality traits you have. These all these kinds of things depend on your nervous system. So the nervous system has three basic functions. Um, Information comes into our nervous system through our senses, first of all. So imagine I'm driving and there are light rays that come from the brake lights of the car in front of me. They would enter into my nervous system through my eyes. Uh, that covers the first function. So it it receives input from the outside world. Your nervous system has to get information through your eyes, your ears, and all of your other senses. Then the second function is that you process the information in the brain by paying attention to it, perceiving it, and remembering it. So after that car brakes and the light rays enter into my eyes, I process that light information by attending to the new stimulus and perceiving. I perceive the information as meaning that the car in front of me is stopping. So the information gets into my nervous system through my eyes. Then I make sense of it. Oh, that car is braking, and so I better do something. So this brings us to the third function. We respond to the information by acting on it. So the car is braking, so I respond to this information by directing my leg and my foot, to step on the brake pedal in order to stop. Um, I would also create a memory of the event. Maybe I later on I go home and tell my wife, "Oh, I had a close call. I almost rear-ended somebody." But these are the three functions. Information comes into the nervous system through your senses. You process it. Um, you know, as long as as long as you pay attention to it, you process it, you perceive it, which means you make sense of it, and you create a memory. And then based on the processing of this information, you respond to it in some way. A bug lands on a bug lands on my arm, and mosquito, let's say, and it bites me. I would get the information from my skin senses. I would process it. Oh, that there's something on my arm. I would respond to it by hitting the mosquito. Okay. Uh, there are two parts to the nervous system. Sensory information comes um, and into our central nervous system, and also decisions come out of our central nervous system. That's the first part. Consists of the brain and the spinal cord. This central nervous system is what it helps us make sense of the world. Um, the nerves that are inside, or sorry, the nerves that are not part of the central nervous system are called the peripheral nervous system. So you have a central nervous system, brain and spinal cord. Everything else is a peripheral nervous system. It's the part that enables nerves to connect the central nervous system to your skin, your muscles, your organs, your glands. And this system helps us to keep in touch with the world. We will look at both of these systems in the upcoming during this chapter. Here is an overview of these two major systems. So on the left, you can see the central nervous system in blue, in the blue box, and it's once again composed of the brain and spinal cord. We'll talk about both of those. One thing to know about the central nervous system is that it's encased in bone. So your brain is inside your skull, which is bone. Your spinal cord is in encased in bone as well. Your peripheral nervous system, however, is not encased in bone. It is that and then once again, it's everything except for the brain and spinal cord. So you can see in the picture on the right that it extends throughout your arms and legs and throughout your whole body, really. The peripheral nervous system is made up of two other major systems: the somatic nervous system and the autonomic. I can't speak today. Autonomic is the word I meant to say. Nervous system. We will talk about each of those in Learning Objective 5, so we'll get to that later. But in the next before we get to that, we'll talk about the central nervous system in Learning Objectives 3, 4, and 5. So I'll start talking about that in the next video. For the rest of Learning Objectives 1 and 2, though, we're going to look at the cells that make up the nervous system. Before I get into the specific parts of the brain and what the spinal cord does, we're going to go down to the building blocks. And these, of course, some of you may know at least, are called neurons. Neurons are the building blocks of your nervous system, the basic units. Just to read what they have here, they receive, integrate, transmit information in the nervous system. They operate through electrical impulses and connect with other neurons through chemical signals. Within a neuron, it operates with electrical impulses. Between neurons, one neuron communicating to another is through a chemical means. And once again, we'll get into all this later. They communicate selectively with other neurons to form neural networks. Neural networks and nerves make it possible for all the complexities of human thinking and human behavior. A couple of things about humans and neurons. So first of all, neurons form what we refer to as nerves, just to make that connection. When you hear about nerves in the body and things like or nerves in the brain, like we're talking about, a system of interconnected neurons. We have roughly 80 billion neurons in our brains, 80 billion neurons. And each neuron has approximately 10,000 connections, with other neurons. So, it's a very interconnected system, 10,000 connections per neuron. This means that there's almost I don't know how often we use this word, but almost a quadrillion connections in the brain. And one little fact about that, according to this guy named Dan Siegel, in his book Mindsight, this was back in 2009. He wrote this. This means that the number of on and off firing patterns in the brain is more than the number of atoms in the visible universe. We have more on and off firing patterns in our brains than there are atoms in the whole visible universe, the whole known universe. Let's take a closer look at neurons and how they work. Here's a nice picture of a neuron. We see a full neuron on the left, half a neuron on the right. I'm going to be using this picture to talk about different parts of the neurons. Let me just go ahead one slide. There's a lot of definitions here. So I will be on the picture as I talk about dendrites in the cell body and the axon and things like that. Just understand that these little definitions are here on the next slide. But I want the picture up as I introduce these terms. So neurons are kind of oddly shaped compared to other cells in the body. They have a number of specific features. And let's just get into them. So I'm going to use a pointer here. Let me set it up. Pointer. Okay, we'll use a little laser pointer. Okay, you can see the red laser pointer, hopefully. So this over here is what's called the cell body. Another word for that is the soma, S-O-M-A. and it contains a nucleus in the center. You can see the nucleus in the center of the cell body here. Um, this this is similar to other cells in the body. I mean, all of our cells have cell bodies, and they have a nucleus in the center. The nucleus is what contains your DNA information. Um, this cell body here, it integrates incoming signals from other neurons. Okay, so it does that using these dendrites that are all around the cell body. Um, these are branch-like, extensions, as you can see, and they receive information from other neurons. I often think of neurons like I often call them communication cells because they send messages constantly between them, and this is what leads to your thinking and your behaviors. It's a whole bunch of neurons, communicating in a sense with one another. Um, so these dendrites receive information from other neurons, and this is a special feature of neurons. Other types of cells do not have dendrites, only neurons. Another second special feature of the neuron cell is the axon, and that is this long tail-like structure here. Um, this is this is what the neuron uses to um, transmit information to other cells. So this neuron on the left is is communicating or sending signals to this neuron over on the right. And so it first of all, remember, in the cell body, it receives information from a whole bunch of other neurons through these dendrites. It integrates the information within the cell body, meaning it kind of sums up all the different signals it's getting. And when it reaches a certain threshold, like there's enough incoming signals, it will send an electrical impulse along the axon, causing these terminal buttons, these little branches at the end, to release a chemical to communicate with the neuron, this other neuron on the right. Um, Axons, you can see this axon has this sausage looking white covering on it here. That's called a myelin sheath. You can see it's listed here. It covers the axon, and it's a fatty substance. It allows the electrical impulse to travel along the axon faster and more effectively. And the way to think about the myelin sheath is it's just like the covering we use on wires um, all the time to so that signals don't get lost. I mean, like if you think about any plug, or if you're, I don't know, if you have something like a charger or whatever, like every there's a wire inside every electrical plug or okay, whatever, inside every plug or any other thing like a mouse cable or whatever. Um, and we cover them, with it's kind of like a rubbery, I don't know what it's made of, like rubbery plastic covering. Because if it wasn't covered, if it's just a bare wire that I had, let's say I had my laptop plugged into, like as the charge went through the wire, it would also go into anything else that's touching along the way. So my cord's like touching the table, and it might be, I think it's my metal lamp. Like the charge would be going into everywhere. If I touch that wire, the charge would go into me. I'd get a shock. So we cover everything so that the charge stays within the cord, and it doesn't dissipate into other things. So this is the same idea. Without the myelin sheath, the charge would go slower. It would be less effective. Some of the charge would be lost along the way. So myelin sheaths are very important for fast transmission of signals within a neuron and within the brain. Okay, so at the end of this axon. I started to mention earlier, these are terminal buttons. And these terminal buttons, these like the ends of these little branches over here, they contain what's called synaptic vesicles. Synaptic vesicles. It's not on the screen here or on the next slide, so it's a new term. Vesicles is spelled Vesicles. And synaptic vesicles are filled with neurotransmitters. The word vesicle basically means little bag. So inside these buttons, these at the end of these little branches, are they contain little bags or vesicles filled with brain chemicals, which we call neurotransmitters. So they're brain chemical messengers that allow one neuron to communicate with another, to send signals to another. Okay, the synapse, they show a couple of synapses here. Synapse, it's basically a narrow gap or space between neurons through which the neurotransmitter, the brain chemical, travels. When I mention neurotransmitters or brain chemicals, we're talking about things like dopamine or serotonin. You've heard of these before. And so there has to be a little gap in order, for the chemical to travel from one neuron to the other. Okay. And that's once again, that's called a synapse. We'll see a close-up of what's happening here in another picture later. Okay, I'm going to move on. Oops. Okay, here we go. I'll just pointer over here. So I covered all these. Yeah, okay. Going on here. Electrical properties of neurons. So part of the neuron, parts of the neuron are covered with a membrane, as it says here, which is semi-permeable. Semi-permeable just means that some stuff gets through, but other stuff doesn't. The easiest way to think of this is like a window screen. It lets air molecules come into your house through your window screen, but it doesn't let bugs get through, for instance. So that's the same idea. It doesn't block everything. It lets some little ions pass through, and in particular, the two of the main ions that pass in and out of the neuron are sodium and potassium. This movement of sodium and potassium in and out of the neuron is what allows it to produce the electrical charge that I mentioned earlier, that travels down, the electrical impulse that travels along the axon that causes the release of neurotransmitters. Okay. Let's go on. The neuron begins in a resting state when the electrical charge inside the neuron is slightly more negative than the electrical charge outside. So resting state means when the neuron's not communicating with another neuron, when it's just, when it's not having a neural impulse, it's slightly negative inside. This is because there's more potassium ions inside, and compared to sodium ions. Potassium ions are negatively charged. Sodium ions are positively charged. So when it's in the resting state, it's slightly negative. When the neuron gets stimulated by nearby neurons, and it through its dendrites, if it gets stimulated enough, it causes what's called an action potential. That's the neural impulse I mentioned. So it's known as an action potential. It travels along the axon and it causes the release of neurotransmitters, brain chemicals, into that little tiny gap, the synapse. So during the action potential, sodium ions continue to enter the neuron. So the positive charged sodium ions come in, and the potassium ions leave, the negative ones leave. And this is what causes the electrical impulse. it was resting at a negative state. Now it gets this influx of positive ions, and the negative ones are leaving, and that's what actually causes. And I don't know the science of it. I'm not. That's not my area, but that's what causes the electrical impulse to travel along the axon. Yeah. After it has an action potential, so it has the electrical impulse, there's something called the sodium potassium pump. Sodium potassium pump, and that helps return the neuron to a resting state. So right after it has an action potential, it has to kind of spit out those positive, to spit out those sodium ions and that had just rushed in, and it allows potassium ions to come back into the neuron. So it goes back to its negative resting state. Okay, that's, once again, we're getting into an area where I don't know all that, the science of how electrical charges work, but let's go on here. This is showing the three phases of neuron communication. So we see two neurons pictured here, and I'm going to blow up the screen here somehow. And where is it? Oh, zoom in. Okay. And I'll blow up over here. So the first three phases. First one is the transmission phase. So this begins when there is enough stimulation collected in the cell body. Remember this, if we saw a whole picture, there would be a whole bunch of other neurons that are connecting to these dendrite branches. So it's constantly receiving signals from you. Remember, from maybe up to 10,000 other neurons. And when it gets enough stimulation, it causes it to have an action potential. The action potential, starts up here in the at the base of the cell body, and then travels along the axon. This was what's going to cause chemicals, neurotransmitters, to be released from the terminal buttons at the end of the axon. So the reception phase is when the neurotransmitters cross the synapse, the tiny gap, and these chemicals fit into receptors that are on the dendrites of another neuron. That's reception phase. So the second neuron's receiving the chemical message from the first neuron. The integration phase is, what is it? Sorry, the integration phase is that this second neuron is going to start summing up this signal as well as all the other ones that it's receiving. When it receives signals, they can be of two types, as it says in this little box here. They can be excitatory or inhibitory. Excitatory makes it more likely that this neuron will have an action potential. Inhibitory signals are telling it to stop having action potentials. And so it sums up all the information it's receiving from all the receptions that are going on from once again up to 10,000 other neurons, and if there's enough activation, it leads to having an action potential, and then it passes the message on. Okay, and then we're back to phase one then. Okay, let's go on. I already talked about the myelin sheath. It's a fatty layer that insulates the axon. To communicate, a neuron fires an action potential. As I said, that's what is going to cause the chemical release, the neurotransmitter release. But some messages are more important than others. Like, if let's say I step on something really hot, I'm barefoot, I step on I step on, something that's like, I don't know, a burning coal or a piece of wood or something, I would get that's an important message for my brain to receive and for me to respond to. And so, we would want, I would want my brain, I would want my brain to receive like a stronger message. But the thing is, a neuron can't fire like strongly or weakly. It it fires or it doesn't. It only has one strength. Think about a gun. I don't like guns, but it's a good example. When you fire a gun, you can't fire it hard or fire it soft. You pull the trigger and it always fires at the same strength, right? And that's the same as a neuron. Um, it can't change its strength. So how does how do we know? What does a neuron do to relay a more important message than a less important message? We're constantly receiving messages from the outside world, like maybe the wind blows through my hair. I mean, that's not really important. I might not even notice it, but I do want to notice when I step on something hot. So think about this. It's and this is an example I just made up. Imagine there's a sentry, like a guard. He's standing up on the Great Wall of China, back in the day, and he carries a gun with him, and every time anyone approaches the wall, his job is to, fire a shot up in the air. And it just lets the people behind the wall know that there's an intruder approaching the wall. And he does this even if it's a little kid that's coming to retrieve a ball, or whether it's an old woman picking flowers, it doesn't matter. It's his job. So if anyone approaches the wall, he fires one shot in the air. And this just, once again, it just alerts you know, others to be cautious that somebody's approaching. Now imagine one day, instead of a kid or an old lady, there's also he sees, coming up over this hill, there's like 1,000 barbarians running towards the wall. And they're all carrying weapons and they're all shouting. It's obviously some kind of attack. I mean, do you think he's just going to do that one firing up into the air? I mean, once again, he can't fire the gun any louder or any stronger. So what would he do? He might be able to figure it out, but you know, he would probably fire that gun over and over again, boom, 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 to show that this is not just a normal, one or two people approaching the wall. This is really important, and that's what a neuron does. Right? It can change its rate of firing. So neurons may fire anywhere between 100 times a second up to 1,000 times per second, and it will depend on the in a sense it will depend on the importance of the message. It fires faster when there's important information being received from the outside world, like stepping on something hot, for instance. In between each of these firings, there's what's called a refractory period. I'm not going to spell it, but it's called refractory period. And this is a brief instant where it cannot fire. So there's always like a little gap in between, a little tiny time gap in between firings. And obviously, like everything is like we're talking, like milliseconds, like because it's firing up to 1,000 times a second, but there's a little gap in between each. By the way, I like to use examples and stuff. Uh, there, there's something else called a refractory period, and it's experienced by males that orgasm, for a little while they can't perform anymore, or they can't orgasm again right away. There's every male has a little time period that it's going to take them to recover before they can fire again, and that's also known as a refractory period. It's like a time where there is no firing that and so the neuron has one too where it just can't fire for a moment. Once again, these moments are tiny small, little tiny part of a second. Okay, let's go on. Okay, go there. Okay, so we have another picture here. So every action potential that happens leads to a release of neurotransmitters, as I've said, that come from the terminal button into the synapse. We see a picture of it here. This is the terminal button from one neuron. This is the dendrite, part of the dendrite of a receiving neuron. And you can see the synapse, the little gap in between. In here, you see a synaptic vesicle. Remember, that means little bag. It's a little bag of chemicals. You can see that it's being released. And these neurotransmitters, they go into these receptor sites, and it's called a binding that takes place. These chemical molecules bind to these receptors. Okay. So once again, neurons do not touch one another, and I will often use language that may suggest that they do, because we talk about you know, connections between neurons and things like that. But when we use that word connections, just keep in mind that there's always this tiny little gap, but it's like they're connected. Okay. These receptors are specialized sites that respond to certain types of neurotransmitters, and not others. So they're specialized. So maybe these receptors, for instance, only respond to dopamine. And so if serotonin happens to be flowing through here, it's not going to trigger them. And so typically, each receptor, site of receptors, they respond only to one specific neurotransmitter. And it's a lock and key system. Like, these molecules fit. You can see, you can kind of, I should blow it up a little. You can kind of see it here. Like, it's like a lock and key system. So it specifically fits. So if these are dopamine molecules, they have a certain shape. A serotonin molecule would have a different shape, and it wouldn't be able to fit in here. Oops, let me go back. Okay, I think I might be done there. Oh yeah, one more thing I wanted to say. The neuron that's sending the signal is called the presynaptic neuron. And they sometimes ask about this on the test. The receiving neuron is called the postsynaptic. So presynaptic just means before the synapse, and postsynaptic means after the synapse. And so pre is the sender, post is the receiver. Okay, let's go on. There's two major ways in which neurotransmitters are removed from the synapse, because they can't just stay there and keep stimulating the receiving neuron, the postsynaptic neuron. After each action potential and release of chemicals, the area's got to be cleaned up. And once again, this is all happening in a tiny part of a second. There are two ways this happens. The first is reuptake, and this is the presynaptic neuron reabsorbing the neurotransmitters. It's like recycling. It's basically recycling. They can be used again. So just to back up, so after this chemical release, and there's activation in the postsynaptic neuron, this terminal button sucks back up a lot of the chemicals that are floating in the synapse here, and then they make a new bag of chemicals, a new vesicle of chemicals, and they can use it again. So that you have to recycle, otherwise neurons would run out of neurotransmitters. There's a second way that we get rid of neurotransmitters in the synapse, and it's called enzyme degradation, and it's just a breaking down of neurotransmitters. These are I don't know, they're just special chemicals. These enzymes, they break down other substances. Okay, and this helps with synaptic cleaning, as it's known. Postsynaptic neurons can produce signals of two types. I kind of mentioned this earlier, so real quick, they can produce excitatory signals that increases the likelihood of an action potential. So it's kind of like one neuron's telling the other one, pass this message on, like get excited, spread this message to other neurons. Or it can be an inhibitory signal. This decreases the likelihood that the neuron will fire an action potential. It's basically this message is like, stop firing. Like you don't need to, pass the message on anymore. Drugs can alter how neurotransmitters function. There are drugs that enhance the actions of neurotransmitters. They're known as agonists. An example is nicotine is an agonist. It enhances certain neurotransmitter action. There are also drugs that inhibit or kind of slow down or stop the action of neurotransmitters. These are known as antagonists. One example of an antagonist is naloxone. Um, that's a medication that rapidly reverses the effects of opioid overdose. It's a standard treatment for opioid overdose. Um, they will try to give you a quick dose of naloxone. I'm not sure if I'm pronouncing it right, but so and what it does is it reverses the effects. If somebody's just had an overdose, it's life saving, and probably a lot of you've heard about it before, but it's the it's what you want to give somebody that's had an overdose, an opioid overdose, as fast as possible, and it just brings them right out of it. Okay, this is a list of neurotransmitters. It's in a chart on page 55. Oh, I also wanted to mention make sure I'm sure you're reading the book, but page 56 is where you can read more about um, agonists and antagonists. This chart is on page 55 in the text. It's a list of some of the common neurotransmitters. I do want to mention that there are over 100 different types of neurotransmitters. I've only heard of about 10 of them. This is a list of some of the common ones that you'll hear about in at least some of these you'll hear about in other parts of the book. Um, so I want you to read about these on your own, and because they can ask you about any of these, I'll mention two things. GABA is the main inhibitory neurotransmitter. Remember, inhibitory is like it's something that gets released to stop neurons firing. There's a lot of GABA released, for instance, when you're going to sleep at night to calm your brain down and calm down the amount of action that's going on. Glutamate, the one right below it, this is the main excitatory neurotransmitter. It um, it you know enhances action potentials. Uh, I'll talk about a few more neurotransmitters on this last slide of this section. And this is from your book. All these pictures are in your book, but I'll just go over them real quick. So acetylcholine these are all neurotransmitters that are listed here. It's responsible for motor control over your muscles. And so what Botox does when you get an injection of Botox, like in this picture here, it basically inhibits acetylcholine, which paralyzes muscles. So you need to see acetylcholine, to control certain muscles. And when they get paralyzed, that's going to stop you from creating like frown wrinkles and things like that. So that's basically what it does. It stops the action of acetylcholine. Just in case, because I never knew how Botox works, so that's kind of interesting. Most of us have probably heard of epinephrine. It is a neurotransmitter that causes arousal, and so when you get an adrenaline rush, it's because of a release of epinephrine within your brain. So we see this picture of a bungee jumper here. Dopamine is responsible for motor control over voluntary movements. And one of the things that happens when somebody has Parkinson's disease, the reason why that they have trouble controlling their movements and they have a lot of twitches and whatnot of their body is because they are dopamine depleted. Parkinson's causes a depletion of dopamine, and so without dopamine, you lose voluntary control over a lot of your movements, and that's why they will involuntarily twitch. Um, Endorphins, these reduce pain. So when you're in pain, you get a rush of endorphins. It helps to reduce the pain over time. And this is why pain subsides, after you have an injury or something. It hurts the most at the start, but then you start getting the endorphins going through your body, and the pain will lessen over time. That will conclude learning objectives 1 and 2.